Greetings of the day to all. I'm Dr. R. Niranjana Devi, currently working as an assistant professor of physics at Fabimycin College in India. I'm very happy to present my paper entitled An Investigation of Topological Electronics Spectroscopic Docking and Simulation Studies of Novel Antibiotic Fabimycin. This is the outline of my study. And the aim of the study is first to understand the structural and intermolecular interaction related properties of the drug molecule and to interpret the electronic properties like charge density and its Laplacian, electron localization function, reduced density gradient, and natural bond orbital analysis of the molecule, and finally to predict the nature and reactivity of the molecule through electrostatic properties, reactivity properties, docking studies, and simulation studies. Let me introduce the drug candidate. Actually, the Fabimycin is a newly developed antibiotic candidate which is effective against gram-negative bacteria, an unusually problematic class of bacteria that uses thicker cell walls and molecular reflex pumps to protect themselves by preventing the antibiotics reaching inside the cells. Actually, this drug can fight more than 300 drug-resistant bacteria. Okay, this is the energy minimized structure of Fabimycin, and this is the stable state structure. And as far as the structural properties are concerned, we can see about the CC bonds, carbon-carbon bonds. They are having their bond length range in that order 1.386 angstrom to 1.519, so which shows that the resonance has occurred among the bonds. And also the C1 atom, which has 3 bonds with the neighboring atoms, which has also the plane angles like 128.16, 115.04 and 116.79, which show the sp2 hybridization and trigonal planar geometry for the central C11 atom. Next we can think about the crystal packing and also the molecular interactions, intermolecular interactions of the particular drug, particular molecule with the neighboring molecules. So for visualizing the intermolecular interactions, the Hirschfeld surface analysis is a helpful tool, and also it shows the contacts of hydrogen bond donors and acceptors. And here the red color circular patches shows the intermolecular distance between two atoms is shorter than the sum of their van der Waals radii. And we can qualitatively as well as quantitatively assess the intermolecular interactions of the molecule with the neighboring molecules. Here we can get the percentage of contacts through the fingerprint analysis. As seen in many other molecules, in this Fabimycin also, the HH contacts plays very important role. Nearly they are having 39%. And apart from that HH interactions, there are OH interactions, CH interactions, and pi stacking also available in this molecule while the packing procedure is concerned. Next we can see about the electronic properties. For the electronic properties, first we can see about the atomic charges. Okay, the atomic charges says that whether the atom is electronegative or positive. Then here we can compare the charges from 3 different schemes like Mulligan population analysis, AIM analysis, and also natural charge. Okay, we can compare and we can see whether which atom is most electronegative and which atom is the more electropositive. Those details we can get from this. And then we can see about the electron density. Electron density is nothing but the electrons per unit volume. It gives us the details of chemical concepts of atom, molecule, structure, and bonds. All the critical points in the covalent bonding regions can be easily viewed through this electron density mapping. And The Laplacian of the electron density gives the details of charge concentration and charge depletion. Okay, most of the time the charges are highly concentrated in the bonding region. So those details we can get out of this Laplacian of electron density map. And the electron localization function also gives enough information about the bonding details, and especially the lone pairs. Here we can see the lone pairs of oxygen atom. The reduced density gradient, it gives the details, and also it allows to identify the covalent bondings, ionic and non-covalent interactions. Non-covalent interactions can be easily viewed through this. Here we can see the strong attraction, leftmost corner. It shows the strong attraction hydrogen bond, halogen bond, and also in the center part we can see the van der Waals interactions, and in the rightmost corner it gives the information of steric repulsion. Then in the reactivity properties, the molecular descriptors such as electron affinity, ionization potential, global hardness, softness, electronegativity and electrophilicity index. So these things, these parameters, these descriptors will give us the complete details of the molecule's nature and reactivity properties. Okay, so based upon all these parameters we can say that this molecule is low kinetic stability and it has high chemical reactivity and it is ready to share electrons. As the softness value is high, this is a very soft molecule. That is an important property for a drug molecule. And also as the electrophilicity index value is low, it is less toxic. That is also a favorable thing of a biomolecule, especially drug molecule. And next we can see about the electrostatic potential. So the electrostatic potential helps us to identify the site and chemical reactivity of the molecule. Here the nucleophilic region, just del minus, which are prone to electrophilic attack, are found near the oxygen and nitrogen atoms, and electrophilic regions, that is del plus, which are prone to nucleophilic attack, are found near the hydrogen atom and the remaining atoms. This can be a good polar molecule because of its high dipole moment value, that is 3.97 dB. Next, the Lipinski rule of 5 parameter gives details about the drug likeness of the molecule. It follows and it obeys the rules, Lipinski rule of 5 parameters. So we can say that this drug molecule is a very good drug molecule and it has much drug likeness properties and all. And in the docking studies we can get details of the interactions of the drug with the target protein, and here the interactions of Fabimycin drug with the amino acid residues present in the target protein can be those details can be obtained from this docking studies. Actually this is a very big area and this is a very big work. I have just presented only 20% of the work, since the experimental charge density analysis is going on, spectroscopic study and dynamic simulation studies are also going on, and is based upon all these parameters we can get details of the structural, intermolecular, topological properties of the drug molecule and global reactivity descriptors. Also using them, the molecule's nature and reactivity and site selectivity we can identify, and especially the lone pairs of oxygen atoms are also can be visualized, and the details about the lone pairs also has been obtained. And also the Lipinski rule of 5 parameter helps to check the drug likeness of the molecule, and then the electrostatic potential helps to identify the sites of electrophilic and nucleophilic regions where the molecular interactions are likely to happen. On the whole, okay, based upon all these things, Yes, we can get a clear description of the structural, topological, electrostatic, and reactivity properties of the drug Fabimycin in a detailed manner, which further will be useful in the design of new potential drugs with improved efficacy and reduced side effects. Actually, based upon the experimental and theoretical electron density calculations, the structural studies and the topological properties and electronic properties, as well as the spectroscopic properties and reactivity properties, we can get a clear picture about the drug. So that will be a platform for the drug engineers and pharmacologists to design new more drugs with improved potential and reduced side effects. So this is the overall idea, and these works are is currently these works have been going on, and these are some of my references. Okay, finally I thank for this wonderful opportunity for the organizers, and also I thank each and everyone for your patience listening. Thank you very much.